Here, that what is a cache? Cache, if we look at the definition of a cache, cache means in the hiding place. Okay, so cache is based on the concept of the principle of spatial and temporal locality. So actually, why cache is there? Because if you look at a microprocessor, the memory latency is very high, in typically more than 200 or 300 clock cycles. Okay, so if we say that we have a memory and which has a very high latency like 200 or 300 clock cycles, like 300 clock cycles. So this is your memory, and let's assume this is very high latency. Assume that this latency is fixed and it is 300 clock cycles. And now you have a microprocessor, and microprocessor wants to read some data. Okay, why the latency of memory is very high? Because the capacity of memory is high. When the capacity of memory is high, so it incurs very high latency. Okay, so now what we do, what a microprocessor do, microprocessor puts a very small memory within a microprocessor, and we call it as a cache. And typically the size of this cache is smaller. When the cache size is smaller, so it means that its latency is
less,
faster. So it's faster. So when it's faster, so let's say if you have a cache within a microprocessor, and now let's assume that its latency is 10 cycles. So whenever an item is referenced from the memory, so not only it brings the whole item, but it's also placed adjacent items. Now I'll explain this with an example. Now let's assume we have a memory, and now we have some block in a memory. We call it as a memory block. And this block size is larger. So now let's assume if we have within this block we have some words, word 0, word 1, and up to word 7. If you look at this word itself is partitioned into bytes. So it's byte 7, byte 6, up to byte 0. Okay. Now if you look at, so word 7, word 6, and word 0. So if you look at this memory block, so this memory block consists of 64 bytes. So now let's say if you microprocessor wants to access some word 3, if you want to access word 3, it not only fetch word 3, but it fetches the whole blocks from the memory and put it in the cache. And it's based on that. So now let's assume we have some access stream. Let's assume we have a memory block I. Memory block I is placed in the memory, and microprocessor wants to access this data. It wants to access word 3 of memory block I, and then it access word 4 of memory block I, and then word 6 of memory block I, and word 7 of memory block I. And these are at different time instance. Let's assume this is time instant T1, T2, T3, and T4. Now if we say that if microprocessor wants to access this data from the memory, and the memory latency is 300 clock cycles, so what will be the latency of this word? 300, 300, 300, and 300. So what's the overall latency? 1200. So if you want to access each and individual words of these blocks from the memory, it will incur 1200 clock cycle latency. So now if microprocessor, now this is the latency to access these 4 data items in the absence of cache. Now let's assume we have a cache. When we have a cache, so actually when microprocessor accesses word 3 of memory block I, so what it not only fetch this word 3, but it fetches the whole block. It fetches the whole block from the main memory and put it in the cache. So when it's accessed, so now in this case now we have an additional latency. Additional latency of 10 clock cycles. So actually when this memory block is accessed, so microprocessor will first look it in the cache, whether it's in the cache or not. So it has some latency. So first latency is tiny. First it look in the cache, this is called as the loop latency. It will look into the cache, it exists in the cache or not. If it does not exist in the cache, it will go into the memory, and the latency now will be 310. So actually it fetched the whole block. So now the block is fetched from the memory W7 up to W0, and it's memory block I. So in this case there is a miss in the cache. When it sees the block in the next time in the interval T2, so for it to look in the cache, yes, the block is found in the cache, so now there is a hit in the cache. So now the latency will be 10 cycles. Again it's a hit, and now it's a hit, so 10 and 10. So now 310, 20, 30, and 40. So the overall latency to access all these 4 blocks is now for 340 clock cycles. So cache is based on the concept of the spatial and temporal locality. So it means that what is the concept of spatial and temporal locality? When a block is accessed, so it is high probable that the adjacent block will be accessed. So it is based on the concept of spatial locality that when the block is accessed now, it is high probable that the next adjacent block will be accessed. So this is the property of program. This is a spatial locality. Which data structure of the application program exploit this locality? Arrays. In the arrays, let's assume you have 100 elements in the array. So if you access element 0, it is high probable that you access element 1. Now let's assume if you have a program, and in program if you want to traverse all the elements of the array, to find the sum of all elements of the array. So you need to access the blocks in sequence. So in this case, if let's assume that if we store these blocks, like all these data items are now in a memory block, so when you access memory block, so return your hit in the cache, and then the overall latency will be reduced significantly. So I also give you an example. Now let's assume if we say that if it is raining in IST, it is more probable that it will be raining in Rawal. But it is less probable that it will be raining in Peshawar. It will be less probable that it will be. So actually if we say, so now if you look at the memory, so now memory we have memory block I. So the adjacent block will be memory block
I plus 1.
and memory block I plus 2. So actually, if we say that if microprocessor accesses this memory block I, it is high probable that it will access the next block. But it is less probable that microprocessor will access
I plus 100.
or this block. It is less probable that microprocessor will access the problem. So this is the concept of spatial locality. Spatial locality is, okay, so how spatial locality? Which data structure of the program exploits spatial locality? Arrays, instructions. Why instructions? Now if you have the instructions are always stored in memory. So microprocessor typically executes the instructions what? In sequence. So actually in instruction I is executed, it is highly probable that the next instruction will be executed until and unless a branch instruction is encountered. So there are two types of branch instruction. It is a conditional branch instruction or unconditional branch instruction. In an unconditional branch instruction, the control is transferred to a further location, maybe a further location. But even the offset, typically the offset field is, especially the jump even within the program is not farthest. It is a smaller jump, not a longer jump. In most of the program, the jump is, and we already did some programs if you remember. So okay, the jump is typically closer. So actually, so this is spatial locality. Another locality is temporal locality. Temporal locality. What does temporal locality say? That if an item is accessed now, it is highly probable that the same item will be accessed in the near future. Okay, which property of the application program is associated? Loops. Now explain this in example. Now let's assume if we have a program statements for I is equal to 0, I smaller than 100 and I plus plus. If you look at this program, now this is a variable I. So variable I is accessed at time ti. For this next iteration, the same item, first what is the value of I? 0. What is the value of I? 1. Now let's assume if this I is stored in memory, this I is stored in this word box 6. I is stored here. So now you are accessing word 6 or memory block I how many times? In this particular example, 100 times. So it means the temporal locality says if an item is accessed now, the same item will, it is highly probable that the same item will be accessed in the near future. Now there is another property of this program. Now let's assume if we say that C is equal to A plus B, this is a C statement, okay, and after some time you say B is equal to C plus 3, and after some time F is equal to B plus A. So now if you look at this program, so this A is accessed at this time and A is accessed this time. So it means that the same item is accessed at time tk and this item is accessed at time tk plus some time. Similarly, C is accessed at this time and C is accessed at this time, and D is now repeated again. So this is also another property of the program. So temporal locality says that if an item is accessed now, it is highly probable that the same item will be accessed in the near future. So the same with the example of the rain. If we say that if it is raining now, it is highly probable that it will be raining after 1 minute. Okay, but it is less probable that it will be raining after 3 hours. Okay, so it's based on the concept. The cache is based on the concept of the spatial and temporal locality. So we exploit this property of the program. Now, if you look at the structure of a cache, so the cache is divided into different sets. In the previous example, we did a direct map cache. If you remember, direct map cache. Direct map cache. In a direct map cache, there was a single cache line in each cache set. But now we are studying in array associative set cache. How many is? Array associative cache. So if you look at the array associative cache, so now the index starts from 0, 1, 2 up to s minus 1. What is s? What is s? S is the number of sets within a cache. What is A? A is associativity. It is called as number of
lines in a set.
cache lines within a set. So now in this example, now we are studying associative cache for direct map cache. For direct map cache, what is A?
1.
A. Each set consists of only a single cache line. So A is 1. When A is 1, so it means each set will consist only cache line 0. Okay, a single cache line. But in this case, how many lines are there? A lines. Now, in this case, we already said that if there are A cache lines, so how the main memory blocks are mapped to a particular cache set. So okay, now I will remove this one. So it means that now in this example, if we have main memory block 0, so main memory block 0 will be mapped to its set 0. Main memory block 1, set 1. Main memory block 2, set 2. Okay. Main memory block A, sorry, not A, s minus 1, s plus 1, 2s minus 1, 2s and 2s plus 1. Okay. What will be the main memory block s minus 1? Okay. What about main memory block S? It will again be mapped to set 0. Main memory block S plus 1.
Set 1.
Set 1. Main memory block S plus 2. Set 2. Okay. Main memory block 2S minus 1. Set 1. What about? Now I'm using different colors. What about 2S?
इधर जाएगा.
Again it will be mapped to. Now if you look at this block, so if we say that the main memory block 0 will be mapped to index 0, main memory block 1 will be mapped to index 1, main memory block 2 will be mapped to index 2. Now it can be written like this: if this main memory block 0 will be mapped, then main memory block what? Main memory block S, main memory block 2S, main memory block 3S, and so forth, so on. Okay, now in this case, since the memory size is very large, and the cache size is very small, so the number of total memory blocks within a memory is very, very large, then the number of cache lines. How many cache lines are there in the cassette? So how many number of cache lines are there? And the size of the cache line is equal to the memory block size. Okay. How many cache lines are there in this set?
1.
No. Total number of cache lines.
S.
No, not S.
S minus 1.
S multiplied by A.
जी sir.
There are S sets. How many sets?
S.
There are, can we say that there are S sets with each set consists of how many lines?
1.
No one. It's indirect map cache.
S set with should consist of
If you look at this set, I already told you it consists of L0, L1,
ठीक है sir. A.
so how can we write?
A.
It S sets with each set consists of how many lines?
A lines.
A lines. So how many total number of lines are there in the cache?
S into A.
S multiplied by A. Okay, now if you look at set 1, to this set 1, which memory block should be mapped?
MB.
Main memory block what?
1.
1. Main memory block
S plus 1.
S plus 1. Main memory block
2S plus
2S
1.
plus 1. Main memory block
3S plus
3S
1.
plus 1. And to set 2,
MB2.
MB2, MB S plus 2, MB 2S plus 2, and so forth, so on. And similarly, if you look at the last one, so it will be MB what? S minus 1,
minus 1.
MB 2S minus 1, MB 3S minus 1, and so forth, so on. Now, if you look at this, okay, now if we take some example. So, now if we assume that S is equal to, let's assume that S is equal to 8. S is equal to 8. So again, the index starts from 0 to
7.
7. So the index will start for S is equal to 8. The index will start from 0 to 0, 1, 2, up to 7. Okay, now it is 7 to 1. So it means that now it will be MB0, MB1, MB2, and MB7, memory block 7. Because now
S is equal to
S is equal to 8. It will be MB8, MB9, MB10, MB15,
15.
MB16, MB17. Now if you look at this example, and now we see this. So now if we have this MB0, main memory block 0, set 0, and to set 0, the blocks that are mapped are MB0, then
MB7.
MB8, S is 8,
Yes sir.
MB0,
Yes sir.
MB8, MB what?
16.
16, MB
24.
24. If you look at set 1, MB1, MB9, MB17, and MB
25.
25. And if you look at so forth, so on, if you look at set 7, so it will be MB7, MB15, MB23, and so forth, so on. Now, if you look at these main memory blocks, now if you look at the binaries of each memory blocks, Now if you look at the binary of this memory block, so if you say for memory block 0, ideally it will be 0, 0, 0, 0, 0, 0. I'm now writing the binary. Then what is the binary of 8? 0, 0, 1, 0, 0, 0. It is binary of 8. Then 16. 0, 1, 0, 0, 0, 0. 16. This is the binary of 0. This is the binary of what? 8. This is the binary of 16. Now you look at this 0, 0, 0, 0, 0, 1. Then 0, 0, 1, 0, 0, 1. Then 0, 1, 0, 0, 0, 1. And if you look at the last MB7, if you look at the MB7, so it means that now if you 0, 0, 0, I'm ignoring the most significant bits. I'm ignoring the most significant bits. Maybe there are 24 bits. So if all of these 24 bits will be zeros. 0, 0, 1, 1, 1. Now, if you look at here, what is the coding for 7? Then 0, 0, 15, then 0, 1, 1, 1, 1, 1. So now this is the code for 7, 15 and 23. It will be 0, 0, 0. What is the code for 23? 23. 15. 1, 2, 3, 4, 15 plus 8. Okay. Now if you look at here, if you look at all of these fields, what is changing and what is not changing? Now if you look at here, if you look at the last 3 bits, they are not changing. Now if you look at the last 3 bits, what does the last 3 bits specifies? What does the last 3 bits specifies? If you look at this example,
Set number.
it specifies the index field. It specifies the index field of the set. Now what is the index field? So now it means that if it is mapped to set 0. Why least significant 3 bits? Why I am considering least significant 3 bits? Because there are 8 sets. If there are 16 sets,
4 bits.
we should consider 4 least significant bits. If there are 32 sets, 5. If there are 64 sets, 6. So now we are looking at the least significant 3 bits of the main memory block address that will specify the index field, and index be specified to which set will be mapped. So it means now it is set what? Set 1. And now set 7. Because there are 8 sets. Now the most significant bits, if you look at the most significant bits, so actually 0, 0, 0, 0, 0, 1, 0, 1, 0. If you look at the most significant bits, 0, 0, 0, 0, 0, 1, 0, 1, 0. So the most significant bits identify the tag field. Now what is the purpose of tag? I will explain it now. Now, can I rub it off? This one, I am now rubbing this off. Now, if we look at, let's assume that the microprocessor wants to access, okay, now in this case. Now, microprocessor wants to access word 7, word 6, up to word 0. Microprocessor wants to access word 6 of main memory block 2. If microprocessor wants to access word 6 of main memory block 2 and it is a miss in the cache, what will happen?
ये मेमोरी को एक्सेस करेगा.
This memory block 2, where it should be placed? It will be placed in set 2 because it is. So now if you look at set 2, the set 2 consists of A cache lines. So now if you cache lines, so we can say, let's assume it is A is 4. Now let's assume A is 4. So now we have cache line 0, cache line 1, cache line 2 and cache line 3. So actually if there is a miss in the cache, this memory block is fetched from the cache. It can only be placed in set 2. It will not go anywhere else. So this is brought from main memory and then put into any of the cache line. Let's say it is placed in memory block. When it's memory block 2, which field of the memory block address will specify where this block is mapped? कौन सी field है? उधर से देखें. The index field. What is the index field? So in this case, if you look at this memory block 2 and if you go on the binary of this, so it will be 0, 0, 0, 0, 1, 0. So this field, the index field specified that it will go to set 2. But now we have another field that is called as the tag field. And now in this case we have, in the cache line, we have two fields. One is called as the valid. Valid means that now it is a valid block. So when the block is blocked from the main memory, so the valid field will be set to 1. Now it means that now this particular cache line now contains a valid entry. And the tag field, now this is the tag field. So now its tag field is set to the most significant bits of the main memory block address. So now it is the most significant bits, and now this is the least significant bit. So the least significant bits of the main memory block address will identify the index field, and the index field will determine to which set this block is mapped. And the most significant bits of the main memory block address will identify the tag field, and it identifies a particular main memory block with a particular set. So now what will be its tag field? 0, 0, 0. So the tag field will be 0, 0, 0. Why this tag field is required? Can anybody let me know why this tag field is required? Why this tag field is required? No, because the number of main memory blocks that are mapped to set 2 are unlimited. Very high. Which blocks are mapped to set 2? कौन से block mapped to? Block 2, then
10,
block 2 plus 8, 10, block what? 18, block what? 26, block what? 34, block what? 42, block what? 50, and so forth, so on. So the blocks that are mapped to this set are many blocks. When there are many blocks, and how many blocks can be accommodated here? 4. You cannot accommodate all, but you have to identify which blocks. Now if you look at the binary of each memory block, so now we go into further the details of this block. So if we go into the binary of this, now I'm rubbing this off. Now we are only considering set 2 now. Now we are only considering set 2. For set 2, memory block 2 is mapped. Main memory block 10 is mapped. What is that? Then 18, then 26, then 34, then 42, then 50. If you look at the binary of 2, so the binary of 2 is 0, 1, 0. And then what is the binary of 80, 10? 0, 1, 0. The binary of 10 is 1, 0, 1, 0. What is the binary of 18? 0, 1, 0. It is 1, 2, 4, 8, 16, 32, 64. What is 18? 16 plus 2?
yes sir.
What is 34?
32 plus
32 plus
2,
2. What is 42?
32 plus 8 plus 2,
32 plus
8,
8 plus
8 sir, 16 आपने ऑन कर दिया.
And now if you look at here, the interesting part is this. The least significant bits, if you look at the least significant bits, what will it identify?
Set number.
The index field. And the index field identify the
Set number.
set number. And what is the set number? Set 2. Now if you look at the most significant bits, these bits, the most significant bits identify the tag field. So the tag field, if you look at the tag field is now 0. If I look at the binary, what is the tag field?
1,
1. What is the tag field?
2,
2. What is the tag field?
3, 4.
No.
ये 1 और 0 सर आपने गलत लिखा है, 0 1 होना चाहिए आखिरी सर,
अच्छा.
आखिरी सर 42 की बात कर रहा हूँ.
Okay, ये इस 10 है ना? 0 1 1 0 and then 1 1. ठीक है ना? So if you look at this, and 0 is here. So this is tag field is 3. So actually the tag field identifies. The tag field identifies which particular block is in the cache. So now, what will be the tag field for my block 0? 0. What will be the tag field? 1. What is the tag field? 2, 3, and 4, and 5, and 6, and so on. So the tag field identifies a particular block within the particular
Line.
set, not line,
Set.
set, because this set can accommodate how many lines?
4 lines.
4 lines.